My thesis deals with dense net approach for estimating infants' limb pose. The World Health Organization defines preterm infants as infants born before the 37 complete weeks of gestation, and every year there are more than 50 million worldwide preterm births. They have a higher risk of an abnormal neurodevelopmental outcome. Hemorrhages, cerebral palsy, respiratory and motor impairments are among the major adverse implications concerning preterm birth. Infant spontaneous motility is a valuable diagnostic and prognostic index of brain lesions, cognitive dysfunctions, sleep disorders, and pain. For this reason, clinicians have to pay particular attention to the monitoring of infants' limb in order to notice an early issue. However, this kind of evaluation is time-consuming, prone to clinicians' fatigue, and susceptible to intra- and inter-clinician variability. During the past year, several researches were conducted to automatically monitor preterm infants' limb pose during the daily routine in a domestic environment. All these approaches were based on wearable sensors, but they show some drawbacks. In fact, they need to be constantly recalibrated, were time-consuming, causing pain, discomfort, and skin damage to the infant, and hindering the spontaneous movement of the baby. For this reason, started from the deep learning approach proposed by Moch et al. In the 2019, the aim of this thesis is the development of a cost-effective CNN-based approach for the detection of joints and joint connection using depth images acquired with the whole-back camera put on infant's crib. The research contribution consists in the introduction of dense blocks in the detection network to improve the performance of previous work. The dataset used is the BabyPose 1. It is an open-source dataset developing in the VURI department. The videos were acquired in the neonatal intensive care unit of the Salesi Hospital in Ancona. The BabyPose consists of 22 depth videos of 22 preterm infants who were spontaneously breathing. For each video, 1,000 frames were annotated, and the annotation was manually obtained every 5 frames. The frames of each infant were used in training, validation, and testing phase. 60,500 samples composed the training set, while 5,500 samples composed the validation and testing set. The BabyPose dataset shows some challenges, such as different pixel intensity levels, the presence of limb occlusion and occlusion due to healthcare operators. There are different number of visible joints in the camera field and a variable distance between camera sensor and infants. The model implemented started from the 2D detection FCNN. It is based on the encoder-decoder architecture of UNET made by 8 blocks. Started from each video frame, 20 separate ground truth binary detection maps are produced. The first 12 for the joints and the remaining 8 for joint connections. The final architecture of the model presents 2 dense blocks along the skip connection. The first one between encoder 2 and decoder 2, while the second one between encoder 3 and decoder 1. Inspired by Wang et al., instead of a simple concatenation along the skip connection of UNET, dense blocks are added, in order to lower the semantic gap between encoding and decoding path. Each layer in a dense block receives future maps from all the preceding layers, and in this way, fewer parameters have to be learned. The dense block between encoder 2 and decoder 2 has 4 dense layers with a growth rate of 64, while the dense block between encoder 3 and decoder 1 has 3 dense layers with a growth rate of 128. Finally, in both dense blocks, a transition layer is added to reduce the number of feature channels. In this thesis, the experimental protocol applied consists in the resizing of the image to 128 per 96 pixels in order to smooth noise and reduce both training time and memory requirements. A joint radius of 6 pixels was selected to build the ground truth mask. For training the detection network, an initial learning rate of 0.01 with a learning decay of 10% every 10 epochs was applied. Moreover, a batch size of 16 and a number of epochs equal to 100 were applied. The detection model was trained using the per pixel binary cross entropy as loss function and the stochastic gradient descent with a momentum of 0.98 as optimizer. The dissimilarity coefficient and the recall were computed to evaluate the performance of the detection network. The box plot of dissimilarity coefficient for joint detection and for joint connection detection are reported. From these pictures, it is possible to observe that the interquartile range for joints was always lower than 0.160, while in the other case was always lower than 0.120. The values of median recall for the 12 joints and for the 8 connections are reported in the table for both models. It's worth noting that in almost all cases the dense network achieves better results compared to the other one. In fact, the dense network reached a median recall of 0.839, while the model without dense blocks obtained a median value equal to 0.806. For what concerns the qualitative results, the model is able to correctly predict even in challenging cases, such as interaction with healthcare operator or infants cross-legs. The testing of the model is performed using the CPU of a mid-range laptop, and despite this, it reached an average detection time of 0.030 seconds per image, so it was consistent with real-time infants monitoring. The method proposed allows an estimate of preterm infants pose in real time and automatically without the aid of a high-performance computer. In conclusion, the introduction of dense blocks along the skip connections allows to improve the performance of the model in the detection of joints and joint connections. The testing of the model performed with a mid-range laptop reached an average detection time that was consistent with real-time infants monitoring. For this reason, starting from this work, it may be suitable for being integrated in a domestic environment to provide assistance for early diagnosis of brain and cognitive dysfunctions. Because of lack of a viable dataset in this field, an enhancement could be the increase of dataset dimensions, and the addition of temporal information would allow to detect the movement of preterm infants. Moreover, this work will be submitted to the 33rd International Conference of the IEEE EMBC. Thank you for your attention.